Okay, we're going to go ahead and get started. Steve is still setting up, so pay no attention to the man behind the curtain there. And I'm going to go ahead and introduce some of the foundational stuff that'll explain some of the things that Steve's showing you. But first of all, first things first, you can't see this very well, but this is a Duke, a Java mascot, and it was 3D printed. Steve 3D printed it, and because I asked him, you know, I'd like to give away a prize at the beginning for someone that can answer a question correctly. And he said, well, just give away this 3D printed Duke, so I'm going to do that. So here's my question. I just played a song, and so I need you to tell me the name of that song and who originally wrote that song. You need to raise your hand. The first, oh gosh, I got 2 raised hands. Oh boy. I'm going to take you right there. Yeah. Very good. Now I wonder if I can throw this to you without being on anybody else. You think? You think I can? Oh, I'll hit you and then you'll pass it over. Ready? Ah, okay. Alrighty. Thank you. What was the answer? It was Taylor Swift wrote it, and the name of the song is Blank Space. You know, I've got a blank space baby. I'll write your name, that one. Okay. All right. But it was covered by a group called I Prevail, I something, and they're a screamo band, and I just really like that particular version. So, I don't know, what do you say? Okay, so somebody's making fun of me down here for saying screamo band. What would you call a screamo band? Anybody? Give me a better name for a screamo band so I don't look so ancient when I say that word. Hardcore? Okay. Maybe I'll stay with screamo. Okay. All right, so this presentation is Raspberry Pi with Java, and it comes in 2 parts, Part A and Part B. Part A I'll be doing. I've got 20 minutes to do that, and Stephen's going to push me off stage in about 20 minutes, so that should be pretty entertaining. That's okay. And so I'm going to give you a little intro to Raspberry Pi and Java ME8, which the majority of the applications that Steve is going to show you was written in. So it's you know, Java, specifically Java ME8, sometimes Java SE8. The hashtag for this is rpijava8, and of course Devnexus. My name is James Weaver. There's my Twitter handle. This is my compadre, Stephen Chin. We both are Java evangelists, ambassadors, whatever you want to call us, for Oracle. And this is going to be based loosely upon a book that we are co-writing called Raspberry Pi with Java. And it'll be out on Oracle Press, McGraw-Hill Education. And that'll be out pretty soon. Steve's got a great profile there, by the way. That's really cool. Yeah, that's okay. That's all right. That's all right. And so that's me. I'm at james.weaver. Don't email me at jim.weaver. Some jim.weaver@oracle.com gets my email and doesn't forward it to me. So if you want me to get it, please email it to james.weaver. And this is also based upon a MOOC, M-O-O-C, Massively Online something course that we created, the evangelist team created, and it's a pretty, I think it's a pretty good kind of primer on developing with Raspberry Pi and Java ME8. It takes you through the whole life cycle, takes you through a lot of different use cases. It's one large kind of use case that shows you a lot of different concepts while it's doing that. So I would recommend that you do that. It's got lots of videos, code, things like that, and I think you'll find it actually pretty useful. And if you want to know where it is, just look for one of my latest tweets, and it just starts out with Raspberry Pi Java Embedded MOOC. It's got the hashtag Devnexus in there, and just follow that link. So the Raspberry Pi itself is the creation of the BBC, the British Broadcasting Corporation. It was commissioned by them in the UK to try to make it more approachable for students to learn to program and to learn to control and monitor devices. So doing the whole DIY kind of thing with electronics. So to make it more approachable, they created a board that costs about $35 US dollars. And it's a board that has everything but the peripherals, and it's got lots of sockets and connections for the peripherals. For example, it's got an old RCA video output, an audio, 1/8-inch audio output. It's got some LEDs, it's got a USB, actually 2 USB ports, a Wi-Fi, LAN, Ethernet kind of cable, HDMI out. It's got a micro USB for power. It'll take an SD card so that you can load the software, the Linux operating system and things like that. And then it's got some pins over there. It's got 26 pins, that version of it anyway. There are new versions, but that one's got 26 pins that have lots of different kinds of I/O that I'm going to be telling you about. And then it's got, that version here has 512 meg of RAM, both in CPU and GPU. So here's a picture of it. Got the SD card over there, the power. You could hook up a USB keyboard and a mouse. There's the Ethernet, and that's the general layout of the board. On the upper left is the 26 pin pinout. Now to develop, you can either use Java SE or Java ME. Java SE is just standard Java. Java ME stands for Micro Edition, and it is mainly for smaller footprint, smaller memory sizes, things like that, as well as applications when you want to be able to connect hardware. It's got lots of APIs in Java ME8 itself that allow you to talk directly to hardware over various different methods like GPIO, which I'm going to talk to in a second, or I²C, which I'll talk about in a second. So Java ME8 is essentially a subset of Java SE8, plus it's got some things specific to talking to hardware. And it's good for things like embedded kinds of applications, remote sensors, meters, gateways, things like that, and Raspberry Pis, and peripherals for Raspberry Pis. So here's the architecture. At the bottom you have, the Raspberry Pi has an ARM CPU, ARM, it's the ARM standard. ARM doesn't actually make hardware, but they have a standard. They have the specs that then hardware makers create, chip makers create according to that spec. So it's, the device is an ARM processor. It runs the Raspbian OS, which is a flavor of OS. And my wife Julie just came in. Hey Julie, come on up here. I've got a seat saved for you right up here with my lunch in front of it. So we'll have been married 40 years here, by the way, in November. So hi, wave hi to everybody. So there you go. She hates it when I call attention to her when she walks in, but hey, you walk in late. I mean, you gotta expect that, right? So, actually, I don't know this person. I'm just having fun. So we've got on top of the Raspbian, we've got a basic set of libraries that implement something called CLDC, Connection Limited Device Configuration, and that has a basic set of libraries and the Java Virtual Machine in it. And then we have a set of APIs that support a wide range of devices. They're called MEEPs, the ME something profile, which talks to different kinds of devices via different kinds of protocols. And then we have some optional APIs, for example, if you want to do file I/O or Bluetooth or whatever. So in the MOOC, in this course that I talked about, it walks you through all the things about installing the Java SE JDK, the software development kit, as well as the ME SDK, as well as NetBeans. In the course we use NetBeans as the IDE, as well as there's a NetBeans ME plugin which has an emulator which makes it really easy to develop and then automatically deploy into the hardware that you're deploying for. So in this case, the Raspberry Pi is hooked up. When you compile and run this application, it deploys in the Pi automatically, so you don't have to kind of FTP it over or something. And in the MOOC, in this course, then it goes through all the steps of configuring the Raspberry Pi for Java development. Now, from a coding standpoint, it's actually very simple. The API has a series of callbacks. For example, you would create, first of all, you extend midlet. So you're subclassing this class called midlet. And then you override the start app method. And that allows you to, that gives you a hook then. When the application is starting up, then you can have it do something. And then in the same manner, there's a destroy app method. And then that is called when things are about to shut down. And so you can do some cleanup, closing files or whatever. So this project that's in the Massively Online course is this idea where you've got this truck that's delivering flowers or vegetables, something perishable, and we want to know through its journey when the doors have been open, what the temperature in the truck has been or in the trailer, and the location at different points in the journey, and what the altitude and location has been. And then we want to be able to log those things in such a way that when it gets to the destination, that we can, with a user interface, some application, can then ask the Raspberry Pi, or the application, where it's been and what the temperatures have been and things like that. And so along the way then, the course teaches you the different technologies up there like GPIO, I2C, GPS, UART, RMS, Record Management Store, and some things about JavaFX. So first of all, using GPIO and I2C on the Raspberry Pi, those are two communication protocols. So in the first part of the lesson then, we're going to discuss GPIO and I2C. So the ingredients for what you'll be, when you enroll in the course, there's a very inexpensive kit that you can get from Adafruit or other Newark or another vendor if you'd like, that has some basic electronic components. Of course, it's got the Pi and some connectors and things like that. And so you have some of the things in the kit are light-emitting diodes, LEDs. And so part of what you'll be doing is using a breadboard and putting those things in the breadboard. This is an LED. If you're not familiar with that LED, there's two wires. There's an anode, which is positive, cathode, which is negative, and that's the shortest wire. And it comes in 3 colors in this particular kit. And then there are resistors, and those provide resistance in the electrical circuit. And so we use them to keep the current at specific levels that are required by the electronics and the Pi itself. And then we have a switch that simulates the door opening and closing. So it's just a momentary on switch. So when you open it and close it, it opens and closes the circuit. And then over on the right is simulation of that. So we've got the switch over, we've got the switch at the top, we've got the power source at the bottom, we've got a resistor over here, and then the LED. And so when you press the switch, it closes the circuit. And then another piece of hardware that we use is a barometric pressure and temperature sensor. And it's a very inexpensive little piece of hardware that does just that. It measures barometric pressure and temperature. And those are the specs for it. So this is the hardware that connects things. You've got your breadboard over there, which you put all your components on, and also this Pi cobbler breakout, you put that on there. You've got some jumper cables that you patch different connections by putting it in different holes in that breadboard, and then you've got a GPIO ribbon cable, and that goes to the Pi from the Pi cobbler breakout. So this is kind of what it looks like with some hardware connected to the Raspberry Pi. There's the Raspberry Pi over on the left with a clear cover, and then here's the breakout board, or the breadboard with the connections in it. At the bottom is on the right is the temperature and pressure sensor. So some things about GPIO. Remember, there are several types of protocols. The first one is general purpose I/O, and that is very discrete I/O, on and off, or you can group some on and offs together to create a port that could have more than 2 values. It could have, maybe if you had 4 I/Os, you could have 16 values. And so those obviously can either be high or low, but it's a very binary thing. So some of the programming there, we use the device manager to open a pin or open a port, and then we can set the value of true to the pin, and if Steve will move a little bit over, yeah, or we could set the value to a port to some hex value, in this case, FF. And then, so we have this interface, and then at the bottom we have a pin listener. So we can set up a listener for when the value of that pin changes, so maybe they've pressed a switch, then it will listen to it, and then you can react to it. So there are several GPIO pins on the Raspberry Pi. Here's the 26-pin connector over on the left side, and this is the map out of the 26 pins. Notice that the ones I'm colorblind, but I think it's green. There are 8 different ones, GPIO numbers, and is it green, Julie? Yeah, okay, it's green, I got it right. Okay, so, I mean stranger, whoever you are. Okay, so I got it right there. So those are the ones that you can play with then and hook those up, for example, to switches or LEDs, things like that, for that discrete I/O. So if I were going to create this application, this ME8 application using a Raspberry Pi and these components to turn a light on and off when I click the switch, normally if I weren't using a computer, I would just hardwire the switch in line with in the same circuit as the LED, hook up the battery, and it does it. It turns off and on. But we're going to implement the logic on how things should be wired up in software rather than in hardware. So here we've got, on the left side, we've got the switch, and we're running it through a resistor to power and a GPIO pin. And then over on the right, we've got an LED, but there's no direct linkage. So where the linkage is going to be is in the programming that senses whether the switch is on or off, or has been turned on or off, or is being turned on or off. And then what we do is going to be determined by the program that we write. So this is just some example code where at the top we're setting up some numbers for those map to the GPIO pins, some of them do. And then here we're creating a GPIO pin configuration, naming a port and a pin, saying it's going to be input only, and trigger both edges over there means that even if I'm pressing down, opening the connection or closing the connection, both edges are going to fire an input. And then at the bottom there, we're opening the device for the button. The device manager is opening something for the button, opening something for an LED, and then we're setting an input listener. And so in the code for the input listener then, if we're looking to see if the value changed, if it did, and if the device is the button, then we're going to toggle the value of the LED. So in software, we have provided the logic for what happens when you press the button versus what happens to the LED when you press the button. So I think I have a video here. Now this will give you an idea of the development life cycle. So here what's happening is we're running PuTTY. You could run any TTY kind of software, but we're logging into the Pi. It's a Linux implementation. It's a Raspbian Pi, or Raspbian Linux. So we're logging into the Pi using PuTTY from the PC, and then we're going to run user test, and that's going to bring up the virtual machine on the Pi itself. So now it's ready to receive programs, you know, for us to download programs into it and run on the Pi. So then here in NetBeans, we're creating an application, and when we first run NetBeans, we run the device connection manager, and we add that device. So there's a device in NetBeans that represents the Raspberry Pi device. And so we're adding it, and then when we run, it downloads it into the device and then runs it for us, and then we can see the status of, you know, everything that's going on in our emulator. And there's the start app method, and here we've got a GPIO LED pin, and then here's just some code that we run for that. So to create a door sensor then, this is the lab that goes through how to do that, and it just extends what I just showed you, giving explicit instructions on what to wire up, and then here's the wiring for it. So it's very similar, except for we have two LEDs. One is red and one is green, and when you close the door, then it's green. When you open it, it's red. So it's warning that that someone has opened the door. And then here's the wiring. So it gets a little bit more complicated. Taking a look at the breadboard, up at the top, the top 2 rows and the bottom 2 rows are all connected horizontally. And so that's how you can easily connect things together. And then the 10 rows, 5 and 5, kind of in the middle, those are all connected vertically so that you can hook things into them and connect them without soldering things together. That's the real reason you use breadboards. You don't want to solder things together prematurely. And so that's what the wiring for this project looks like. So then now we'll switch gears to I2C. So GPIO is discrete I/O, either on or off, or you can combine some together. I2C is kind of a bus architecture. And so to demonstrate that, we use this hardware that's, this is where we're using the barometric pressure and temperature hardware. And it's a synchronous protocol, and you have data being sent from one device to another. You can have them in a chain, in a bus, and then you have a clock and a data signal. And so I2C stands for inter-integrated circuit. It's also called a 2-wire interface, and it's a multi-master serial single-ended computer bus. So Philips created it for being able to attach peripherals, like low-speed peripherals to cell phones and other mobile devices, and then control them. And so you have 2 bidirectional lines. One is the data line, one's the clock. So here's a kind of a pictorial view of it. And so any one of these can be the master, and then you have clock signals, and then you're communicating data between any 2 of them. So, or putting it on the bus. And so this is how we wire it up. You've got voltage up at the top, you've got your pin for data, you got your pin for the clock, and then you've got ground. And then each I2C device has an address. In this particular case, we've got 77 hex address, 77. And then you use 7 bits for device addresses. So you can have, 127 devices on a bus. And then there's a control register and a temperature value register. The control register is for being able to say, I want the temperature or I want the humidity. And so you put that request on the control register. And then the temperature value, maybe if I've said I want the temperature, then I'll read the temperature register to find out what the actual temperature is. So here's the wiring for that. And then here's just some sample code for being able to do that. Here we're setting up those values at the top, opening the device, and then here we're writing the F4, that's the control register, it's 1 byte, and then we're saying get the temperature, 2E means get the temperature, and then we're reading the FX there, or F6, that's the temperature register. We're reading 1 byte into the buffer, and so after we've done that, we could look at what was read into the buffer and find out what the device reported for as temperature. So then, so after GPS, and are we just about ready? Yeah. You are ready? Okay. So I'm going to tell these nice folks really quickly about UART to complete the, the 3 protocols. Okay. All right. So, so the last thing I'll tell you about is UART. So that's, who remembers the old Hayes modems? Okay. All right. Well, so who remembers 9600 baud Hayes modems? Okay. Now take your hand down or leave your hand up if you remember 4800. Leave your hand up if you remember 2400, 1200, 300. Okay, who do we got? The gray-haired people. Okay. Does anybody remember 110 with acoustic couplers? Do you? You do? Okay. All right. Nice. You don't look old enough to remember to remember a 110 with acoustic couplers. Wow. Yeah, you could tell some stories, I'll bet, with those things, right? Yes. Has anybody ever we're way off topic, I'm sorry, but anyway, I have to ask you, since we have so many that remember 300 baud modems, has anybody ever, with a 300 baud modem, called it just to hear it, and then whistled and to make it think that you're a modem, and it actually throws back a signal and tries to send data to you? Who's done that? You've done that? What other weirdos have done that beside me? Yeah, you too? Okay. Yeah, exactly. Exactly. That was actually great fun. It's like, wow, because you're coding all night, you're getting lonely, and well, maybe that modem will talk to me or something, right? Yeah. So the last thing I'll tell you about is UART, and so UART is a throwback to those days, right, where it's stands for something that begins with UART. Serial. But it's serial. Just call it serial. And so we're going to talk to the GPS with that. So you have a little GPS breakout board. There we go. Universal asynchronous receiver and transmit. It's serial, and there's the standard speeds. There's the protocol. You can have 7 bits. You could have 8 bits, I think. If you want a parity bit, 1 or 2 stop bits. Am I bringing back memories? Should we talk about VT100 terminals? Anybody? Anyone? Okay. And so UART is a standard, and it doesn't actually usually drive the transmission of data. There's, you've got RS-232 and 422 and things like that actually do the transmission of data. And the transmission doesn't even need to be electrical. You could do UART over Bluetooth. So GPS in this case study with this class, there's a GPS board, and it communicates, or it receives its location if it's got 3 or more satellites, and you all know about GPS. If you have a 4th satellite, you can calculate altitude. And it's a text-based protocol, and you talk to the GPS board via this text-based protocol, which is UART. And so you can connect that one of two ways with the Pi, either through the USB, one of the USBs, or you can directly connect it with, so here's, if I were going to use USB port here, I would use the USB adapter, which comes to, there are 4 wires there that go into TX, transmit, receive, ground, and VIN. What's VIN, voltage?
Voltage in.
Voltage in, yeah, there you go. And then also, I could use GPIO connections. So maybe I don't want to use the USB on the Pi, maybe I want to use the GPIO pins. And so I would use those pins, 14 and 15, those are the UART transmit and receive. And that's how we connect it if I want to use the GPIO pins, the UART pins to talk to the GPS board. And so I think I'll leave it at that, and I will now introduce my co-speaker, the illustrious Stephen Chen.
All right, thank you very much, Jim.
Can I go down and talk with my wife?
Yeah.
Do you need me up here anymore?
No, well, I may need you for the car in the back when we're having fun. You're okay with fun, right, Jim? Okay, so Jim was actually teaching you stuff, and I don't actually promise you'll learn anything, but hopefully we'll have fun. Is that okay? All right, so I have several different demos, so this is like a demo speed run. And we're going to see how many of them we can actually get working in the next 40 minutes or so before the session ends. And as you saw me fitzing on stage here, one of the great joys of owning a 3D printer is it never actually works when you want it to. So anybody own an Ultimaker in the audience? Okay, a few. You know the atomic method? No. Okay, it's a good technique. I'll teach you it later. That's how you unjam your printer on stage very quickly. Named after Atomic Bob on the forums, the Ultimaker forums. All right, so we even have a slide deck. And I don't know about you guys, like I'm pretty thirsty, and I could use a good cup of coffee. Have you guys found any really good coffee at the conference? How's the coffee they're serving out there? It's warm. Okay, well, you know, we're Java engineers. Oh, how do you like my desk? We're Java engineers, and I think we can do slightly better. We're going to see if we can't brew some coffee on stage here using the hardware that I have on hand. And I actually did a little research because being a proper Java snob, it would be completely inappropriate if we didn't have some local Batdorf and Bronson Java coffee to work with, right? Anybody a Batdorf and Bronson fan? I think they do what's the name of the chain? Goat? Yeah, Dancing Goat. So they have a couple stores, Dancing Goat. It was really hard research. I had to drink a lot of coffee yesterday. And actually the owner, well, I guess proprietor owner, I don't know, the guy who was there, Mike, was really helpful. This isn't Mike, but he has a cool t-shirt. He was actually operating the coffee machine. Here's a video. Let's see if it plays. So after they do the roasting, they let it cool in a big bin, and they suck it up into this vacuum tube. And I'm getting great sound, but no picture. That was awesome. And then here's Mike, who was really awesome. So literally, Tori, who's the voice of Java, and myself, we bombed in on Batdorf and Bronson's plant yesterday, and we said, Tor, we're from this super important geek tech conference. You have to give us a tour right now. And he did. He was awesome. And he even gave us some free coffee to boot because he had no idea how to sell us coffee. All right, so to accomplish this, I'm gonna need somebody with specialized hardware in the audience. So does anyone have a ceramic mug? Okay, so I saw a hand go up in the back. You have a mug on you. You were hired. Please Please come up and help me out here. And I also, I need somebody who, well, I wouldn't say strong, but patient. We're going to fresh grind coffee, so this requires patience. Anybody patient? Okay, sir, please, come on up. Yeah, so just come on up on stage. Sorry, the stairs are on the other side, but you can walk up. Oh, wow, this is a really nice Thompson Technologies. Staffing. Okay, so we can thank the vendor who's given out this. That is awesome. We can also thank my hotel where I stall their water boiler. Oh, no. So hopefully the police aren't there when I get back to my hotel. And then we have some water, and we even have an IoT application to go with this. If you see me juggling my hat precariously here, you'll find out in a sec. Okay, so any good demo needs a real IDE. We're using NetBeans. And all of this code was prepared well in advance, Sunday actually. And it's wonderful because it kind of worked when I was at the Greenville Jug, great user group, and it will hopefully work now as well. Okay, so we got our Java Scale project, and it is all of 280 lines of unoptimized code, so it's probably about 100 lines once I actually finish it. And basically, it communicates via this little weighing scale, the Dymo scale, and it's going to guide us through the steps to brew the perfect cup of coffee. So let's kick it off. NetBeans has nice remote debugging support. So you just set an embedded JRE, which it connects to. It's trying to connect to that now. And then once it connects, it'll deploy the jar file. So compile locally on your machine, because your machine is much faster than the Pi, deploy the jar file. And now it's giving us instructions which are covered by the 3D printer. But I think we'll go with it. OK. So you get to, as our, come on up. You guys both need to help out. So what's your name?
I'm Kim.
Kim, good to meet you.
Hi.
Hubert. Hubert? All right, Kim and Hubert. All right, so we have a few different brews for you. So you guys are more like Guatemala, Costa Rica. This is organic Costa Rica. So this is what Mike gave us. And then we have the Java, which I tossed somewhere. You guys are pointing this way. OK, here's the Java. So what do we want? What do we want to try?
Costa Rica.
Costa Rica. OK, that's actually a really good choice. Mike agrees with you. All right, so here, get a whiff of that. It's good. Fresh. All right. So we've got this, and we've got the torture device for Hubert. This is your torture device. But before we do that, why don't you measure the beans? So pop that on the scale. Put it over here. And what did we say? 17 grams? 17 grams of coffee beans. And it's not going to let us go a single beat farther until we get our 17 grams. So here, give it a try. Try to measure about 17 grams in there. You can cheat by looking at the numbers on front. OK, and while she's measuring that out, so it's a little hand grinder by a Japanese company. Nice ceramic conical burr grinds for our coffee snobbery. And it takes a really long time. You have to crank this for days. I did this morning for my cup of coffee, and it wasn't worth it. I'm going straight back to Starbucks. All right, how are we doing? Pretty close? Oh wait, no, it says you're done. See? Great. You can take your coffee off the scale now. Actually, I put a tolerance of 1 gram up or down. We can't tell the difference. OK. So why don't you grab this? Here's your beans. Just pour them in the top. All right, and you probably need this. Pop the top back on as well. All right, and just so we don't overdo it, I'm going to make sure we have about the right quantity of water. I'm going to cheat a little. All right, there we go. All right, so time to brew. Drop your AeroPress on. Anyone used an AeroPress before? So this is like, hey, you guys like it? Yeah, I mean, it's the ultimate travel maker for people who like espresso or even American coffee. It makes a good cup of American coffee. Very convenient and very cheap as well. So the way this works is there's a plunger, and it just goes through. And then we're going to do the upside down method. We're going to do it the gourmet style. So you put it upside down, you put the grinds in, and then you stir it with the water. And then we're going to put it on top of your beautiful mug and then push it.
Okay.
Okay, so here, pop this on the scale. Then we're going to fill it with grinds when he's done, and then we're going to press the tare button. And when the scale goes back to 0, the program will know to tell us what to do next. It's actually going to time it. It's going to count down from 60 seconds so we get the optimal brew time on our coffee. How's that? How's it going, Hubert? You'll know when you're done because it'll be easy. Keep going. Patience. If you're like, you know, seriously need a cup of coffee in the morning, this is not the way to do it. Oh, and actually, we have a beautiful Batdorf and Brunson mug as well we're going to use for this. So we can just press right on the mug. Okay, so our hot water is ready. Come on. Holding things up. We're never going to get out of here. That's the excuse I'm going to use when the next presenter walks up and I tell him I need an hour to tear down everything. We'll blame you. It sounds like it's almost done, actually. And do you like your coffee strong or weak? Like, do you like American style or espresso style, personally?
I don't really drink coffee.
You don't drink coffee. How about you, Hubert? Okay, so maybe tea. You're going to use the mug you got from the vendor for tea.
Yeah.
Okay. I do like good green tea. And actually, our new project for Chapter 7 is one of my buddies in, you're done. You're definitely done. One of my buddies in Taichung runs a tea farm. So I'm working with him, and we're going to do some soil monitoring of his high mountain tea. It's on the Lisan, or which mountain is it? I forget. But yeah, he has good tea. All right, so please do the honors and, where is it? Dump the grinds in the AeroPress. Perfect. We're going to cheat and use this as a stirring rod. And I'll add the water for you because this is actually the hardest part of this whole thing. Okay, so give it a stir. Oh, okay. Well, maybe the water wasn't quite the right. Oh, I know what. I forgot to press the tare button. Yeah. Okay, well, just keep going with it. 60 seconds. And we should have a perfectly brewed cup of coffee. Let's see. You guys see the water? Yeah, this is the best way ever to kill time. Highly recommend it. We'll get to the Ultimaker in a second. All right, I think we're good. We're good. Okay, just dump that on the table. Very hygienic. Pop this on. Okay, now the trick with this is the moment we flip it over, it's going to make a mess. But you want to try giving it the push? Here, I'll hold the mug for you. And just flip it on top and then push it down. Push the plunger all the way down. Oh, wow.
What?
Keep going. Yeah, that's good. See, I think we got 9 bars of pressure, right? All right. You want to give us a hand, Hubert? Oh, yeah, okay. So that little hissing sound means all the water's through. Okay, I think we're good. All right, so neither of you drink coffee, right? You want to taste your hard work?
I'll drink it.
You'll try a little? Okay, so this is going to be strong.
No milk in it?
No milk, no milk. Straight up, straight up. Actually, well, this little side story. So the first coffee I... All right, give these guys a round of applause. All right, so thank you guys. Thank you guys.
What's that first step?
Yeah, okay. So anyone really want the coffee? All right, I'm gonna down it then. Let's see how. Oh, did somebody say they wanted it? No. No. Let's see how it came out. Has a good smell. Actually, it's pretty good. I expected it to be a little sour, because that's what happens when you under-extract it. But I think, if anything, it's slightly over-extracted, like a little slightly on the bitter side, because we didn't have the timer going when we were doing it. Okay, so now I'm all charged up for the presentation. We can forge onward. And the next thing we're going to do is we're going to do some racing. So we have our racetrack set up. Sorry, people. This is also, I should have said this at the beginning. This is the sort of presentation where you're not required to sit in your seats. So feel free to move around the room or get a better view or whatever you stretch, all that stuff. And we're going to do a driving test. So I was doing a lot of hard work in preparation for this. I played a lot of Mario Kart with my daughter. She's 11 years old. She beats me all the time. It's really sad. But I actually think kids these days are spoiled, because in comparison to like the original Mario Kart, this game it's so easy and forgiving. And I pulled out my old Nintendo. I had my parents ship it to me, actually. And I did some hard training for this. So I got Mario Kart. Any Mario Kart fans? Yeah, it's actually, Rainbow Road is impossible. You fall off and you've lost the race. Ninja Gaiden? Yeah, and this is, how many of you people actually beat Ninja Gaiden? Yeah, you're shaking your head, okay. That's hardcore, because this is like at least a week of not turning off your console and throwing your controller around. It's really frustrating. This looks cute. No, Mega Man 1, evil. Like completely unbalanced, awful enemies, bosses. Dr. Wily doesn't die except to one random weapon that never hits him. It's horrible. Gradius, some good survivability. And then I came to Nirvana. Anyone know what this is? Konami Code. All right, so one of those people who said it, I challenge you to a race. We're going to do some racing. So I've got a platform here. Who wants to race me? All right, sir. So we've got an IoT car, tank of sorts, and we have a controller here to control it. Okay. The basic controls are, you have to kind of aim at the IR remote in the back, but the center button makes them go forward or stop. So you press it once to go, once to stop. And that's pretty much how all the controls are. You press left once to go and once to stop. Press right to get once to go, once to stop. And if you're going, then you can press left and it'll turn, and forward and it'll turn, like that sort of thing. But if you press the same button twice, it'll stop. Okay. So forward, left, right. There's also a backup, but you're an expert. You won't need that. And anybody have a stopwatch on them who can time? Cell phone? Cell phones are like stopwatches. You got us, man? Yeah. Okay, thanks. So we got our official gatekeep timer. You want to do a little warm-up with the controls and get comfortable first? Sure. My recommendation is if he runs away from you, just get closer, because sometimes the IR doesn't actually reach that far. Gotcha. Like here. Oh, actually it works. Wow. Oh. I think you need to use a backup. Yeah, backup. Yeah. All right, so we got a timer. Okay, so right here at our mark, the Cobb Galleria Center Coffee mark. and 1 revolution around the track, and tell him when to go.
Ready, set, go.
That's okay. I'll give you a handicap there.
Style points, right? If he goes off the track, does he have to start over?
How about for me, we'll make that rule. If I go off the track, I'll start over. That sound fair?
It doesn't like turning right.
Oh.
It's like a NASCAR driver. It has to turn left.
All right, what do we got? 45 seconds. All right, and let's see how I do. Now, oh, actually, that's cheating. We gotta be behind the start line. Okay, so ready?
Set, go.
All right.
When you stop it.
So just to be fair, I'm gonna close my eyes and see if I can get it. How am I doing so far?
Good.
Pretty good?
Yeah, on the time.
Oh, I peeked a little. Sorry. All right. I think I'm not cheating quite enough. Let's increase the cheat level.
Way ahead so far.
All right. How'd I do?
27.
27? Okay, not bad, right? All right. So actually, I cheated. So as you might have guessed, this guy's a line follower. And I also didn't tell you about the speed buttons. So I double cheated. All right, so give him a big round of applause. Thank you. All right, so this little guy, he's actually made with the MakeBlock hardware, which is it's kind of like aluminum Legos for big kids. Well, all right, we'll just let him run. It's kind of like aluminum Legos for big kids. And it integrates really well with Arduino and Raspberry Pi and all the different embedded boards. They have a really nice shield platform, so you can see on top of the robot there's a nice shield with convenient jacks. Okay, so our buddy Mr. Grabby. And what I did is I under the Arduino Shield, rather than putting an Arduino, I put a Cooking Hacks Shield, which adapts from the Raspberry Pi GPIO pins to the Arduino pins. And then put a Raspberry Pi under that running Java. So all the code for actually controlling the directions and the logic is done in Java code. The company which makes the MakeBlock stuff is based out of nearby Hong Kong. It's like Shenzhen. It's like the island near Hong Kong. And they also have a 3D printing platform and a whole bunch of different things which they do with their aluminum construction. But one of the cool parts about it is that the way they design the aluminum rods, well, first of all, they're more sturdy than Legos. So this can actually stand falling off the stage. He's fallen off the stage before. Can stand traveling around in my cargo cases all over the world without getting decimated. My Lego Duke, which I showed here last year, I believe, he is currently in pieces on my workbench at home. He's not as happy as this guy. And also, it's fairly configurable because the rods, they have like a horizontal cut in them, and then little rivets which you can screw into, little rails which you can screw into perpendicularly. So anywhere along the rail, you can actually put screws without a nut. And then you can also do butt ends, and they have holes on the side as well for attaching points. And they use plastic pop rivets that you can attach two things flat on top of each other. So it pretty much lets you build almost anything, but with a very rigid, sturdy frame, where you can even use it for like 3D printing or advanced purposes. So cool platform for building stuff, and a great application of the Raspberry Pi. So here's the belly, batteries and motors, and then a little bit about the line follower. So if you notice, the track is white with a black center strip that it's following. If you were doing this on, a pretty white ground surface or a pretty black ground surface, you could just assume that was ground and then have a single strip of white or black in contrasting color. And this is really accurate. So it uses, a little infrared transmitter or receiver, and it bounces it off the surface, and it can accurately detect white or black colors. And there's 2 pairs of them. That way, when he goes off the right side of the track, he knows to turn left. When he goes off the left side, he knows to turn right. And fairly fast as well, as you can see. Huh. Still going? OK. That's the longest I've let him run. We'll see if he actually falls off. This is a little bit of code of how you would get GPIO using the Pi4J library. So it gets 2 pins 13 and 14 for the 2 line followers. The way the line followers work on the MakeBlocks platform is it's a digital input. Each of the infrared LEDs is either on or off for whether it sees white or black. And then it gets the 2 sensors. And based on the value of the sensor, it will either turn left or right. So I think the whole code, it's checked into GitHub. If you check my GitHub repo, github.com/steveonjava, you can check out the source code. I think it's only maybe 100 lines of code or so. It's pretty short. Very easy to use. Oh, there we go. GitHub repo, information about what you need to build it yourself. And this will be one of our book projects. I forget which chapter. For the book, actually, I'm going to upgrade him slightly. There's a new serial Raspberry Pi Shield that they have, and it gets rid of the need to use a USB battery to power the Raspberry Pi because it adapts from the 12-volt current coming off the batteries into a 5-volt current for the Raspberry Pi, so you can power the Raspberry Pi off the same power supply as the motors. And it also gets around adapting Arduino pins to Raspberry Pi pins, which basically, like with that level of indirection, with the shield and then with an Arduino Shield and an adapter in the middle and then the Raspberry Pi below, you basically need to read 2 wiring schematics, one for theirs and then one for the Shield, to figure out which GPIO pin or which of their pins corresponds to which Raspberry Pi GPIO pin. So that's documented in the code for all of the pins, actually. I just went through and figured them all out. But I don't think you need to do that anymore with the new serial connector, which they're selling, which I think is a better solution. So that's what we'll be using in the book. OK, so how about some magic? Yes. Yes. All right, so for this, I need some volunteers to help me out. Let me see, did I have anything exciting? OK, yeah, that's the slide. So I have some playing cards with me because there's no chance anybody in the audience would have playing cards, but just verify. These are normal playing cards, right? Yep, nothing special, nothing. They're laughing. And we need some volunteers from the audience. So about 4 volunteers. Who would like to? Please? OK, come on up again. Who else would like to come? Yes, sir? And one more. OK. Let's go. 4 volunteers. Now, unfortunately, my magical powers are running out of battery. So we're gonna leave the magical hat right here, hooked up to USB power for a bit. But that's OK. Just pretend that the battery wasn't actually out of power, and it'll be great. Oh, and we have another project. Let's run this guy. All right, so that's just the man behind the scenes. You can ignore all that. OK, so who wants to be the card giver? Who likes giving? You like giving? OK, we'll make you the giver. OK, so let me get the jokers out of the deck because they don't actually work.
Do you want me to shuffle?
Oh yeah. How about it? Give it a good. No cheating here. We don't want to. You've seen that clearly. I'm an upstanding presenter. I would never cheat you guys. OK, excellent. So here's how it goes. Drop a card in the hat. And then one of you guys can pick it up. Anyone? You want the card?
Okay, what do I do with it?
Well, did it fall in somewhere funky? All right, hold on.
Oh, inside.
OK, we're going to try that one again because Oh, you already got the card out.
Yeah.
Okay.
Okay.
But yeah. All right, drop the card in again. Okay, now you can pull it out. All right, let's try the next card. Drop a card in. There you go. Grab your card. All right, your turn. Card. All right, so I'm going to use my powers of deduction here to try to figure out what you are. So what's your favorite number? What's your favorite number, Jim?
7.
7. No, try again.
3.
3.
I love 3.
You love 3. Yeah, that's my favorite number too. But hey, Julie, has Jim done anything really nice to you here? Did he give you a nice, heart, maybe? Yeah, that's very romantic. These guys are actually traveling around the world together, which I think is great. 3 of hearts, maybe? All right, one down. Okay, so we're going to stop there. So basically, thank you guys. All right, so let's see. How did we do? Queen of diamonds, 6 of club. Okay. So thank you guys very much for playing along. This works a lot better when the hat's not tethered facing the screen, where they're staring at the cards as well. But if you look closely at these cards, I'll pass one on each side. Just try to make sure it makes it back so I have a full deck. If you hold it up to the light, you can actually slightly see the RFID tag inside of it. So it's got a Me Fair Ultralight RFID tag. And I'm using PNC 532 chip inside of the hat to pick up which cards dropped in. So when you drop a card into the hat, it's picked up by the RFID reader. It looks up in a properties file according to the ID which card it is, and then returns that to a program. So these are actually used for electronic poker tables. That's the most common use case for these cards. But they're also really cool for playing around with for home automation. You could have like a card to open your door, or you could even create your own electronic poker table for probably a less cost than they're going to charge you for a commercial solution for the same thing. The actual hardware here inside of the hat, I have a close-up shot, and I'm going to pass the hat around as well. So he is an Odroid W inside of it, and it's running off of a little battery, which doesn't have too much power left, but he's still going. And it has you can also see the card reader inside of it too. So I'm going to pass this around so you guys can see the hardware inside the hat. And unfortunately, the guys at Hardkernel at Odroid, they weren't able to buy the chips anymore from Broadcom. So this is a Raspberry Pi compatible board, but they couldn't get Broadcom to sell them the chips. So what we're going to substitute in the book for this is we're going to use a Raspberry Pi A+ instead. I don't know if you've seen them, but they're a little bit smaller than a standard Raspberry Pi, and they're really good for small embedded applications like this. But exactly the same software that runs on Raspberry Pi like B or B+ will also run on this Odroid W and the Raspberry Pi A+. Okay, and there's a close-up of the Odroid W and the card reader on top taped into the hat. The card reader can use I2C, SPI, or UART as the communication medium. I've tried 2 out of 3. SPI and UART work. I tried I2C, but my board is broken. Apparently, a certain number of the boards from Adafruit don't support I2C due to some defect, and mine's one of them. So I can do 2 out of 3 protocols. You can tell it's a device error because it doesn't show up as a device even into Linux. So it's not even communication from Java. And then for the NFC configuration, I used libNFC, so a standard NFC library, but in between I use IDF NFC as a layer. So Java, the normal Java NFC APIs, which are part of SE, can communicate directly to the card. Without this extra layer in between, you would have to write like JNI calls to libNFC, which would be a lot uglier. This way you get nice clean code. You're using the standard Java SE API for card readers, but you can use it on a Linux platform. Okay, and there's the code, getting a card terminal, waiting for the card, and then reading the data. And like, I think this code ended up being like 80 lines, 50 to 80 lines. Really simple. If it isn't already in my GitHub repo, it'll make it there soon because I actually have to, I think this is chapter 4 in the book, which I'm due to do in a couple weeks. Okay, and then last topic is 3D printers. So you're probably wondering what relevance do 3D printers have for Java, right? Maybe? Well, they're cool. How many folks have a 3D printer yet? How many folks wish they had a 3D printer? Okay. So I would highly recommend it after having, this is officially OTN's printer, Oracle Technology Network, but since I'm the only one who knows how to run it, it's been in my house most of the time. And after having had it, I would actually pay my own good money to buy one. I think it's worth it. So it's really cool because you can actually, well, you can build cute things like these elephants are off Thingiverse, and they were designed by some guys in Europe after like a public park, which has a movable elephant slide. But it's a really cool design, and there's lots of things you can just print for fun. I'll pass these around. They're a little bit delicate. Try not to mangle them too much. If you drop the large one on the ground, his nose will break. My young daughter has proven that. So you can print lots of cool stuff with it, either off Thingiverse or using different libraries, but you can also print directly from Java code as well. So what I'm printing on the printer now, and I think it'll even finish before the presentation's over, is a Raspberry Pi case. And this Raspberry Pi case is defined using Java geometries. So it creates rectangles and spheres and subtracts and adds them to create the final geometry form, and it's all expressed in normal Java code, like code that you could easily read and write, which is a really cool way to do precise mechanical structures like this. The 3D printers are actually really good. If you have something which has exact tolerances on it, you can pretty much print it. Like I did a little wearable keyboard, and I form fit it for Cherry MX switches. And I basically, from the specs, took the size of the Cherry MX cut out on a board and then laid it out, and it fit perfectly once I 3D printed it. So it's really good for doing mechanical prototyping, doing little embedded cases, really helpful around the house. You can, all sorts of uses, like little door holders or finding things in the kitchen where you can actually effectively meet exactly what your space or your environment needs. And it's really simple to like invent and create and print things yourself. So I highly recommend it. So what I've been using is the Java Constructive Geometry Library that Michael Hoffer wrote. He's in Germany and works for a university. And basically, you write Java code. It has a little visualization of what's going to be printed. And then it generates an STL file, which goes to the 3D printer. So STL is the standard 3D modeling format that 3D printers use. And then the same format you download things off Thingiverse, for example. And then you use a slicer, like I'm using Cura, which is made by the Ultimaker guys, to actually do the slicing into commands that the printer can use to print things. So references for that project. But let me, since all the other demos worked, I have to have one last chance to fail, right? So we will do the demo of the actual 3D printing software and see if it comes up. So this is straight out of the repo. I synced the code. The build failed. I'm doing pretty good so far. Let's see. Folder. Task run not found. OK, wrong folder. Do-do-do. Okay. There we go. Second error. But I knew that was going to happen because we didn't have an internet connection a second ago. Now we do. Gotta love Maven/Gradle. Great fun. OK, and we have a working code editor. And basically, this is super simple. It's a big, well, cube with the sphere subtracted. So what do you think happens if we make the sphere smaller? Anyone? OK, well, that was too small because now it's completely inside. Make a little bigger. Now we can see we're like a really tiny cutout of the sphere. And if we make it bigger, at some point, the sphere will go away. There we go, gone. So we now have like an empty geometry one. But you can see it's really easy to write your own geometries and then visualize what they are. And as an example, this is the board mount, which I'm printing here currently. So it's basically a very simple geometry. It has a bunch of these pins defined, and it reuses the same pin code around the perimeter and just rotates it and transforms it. And then it has a base, which is basically a rectangle or I don't know, what's that called? A non-sphere, a box subtracted from another box. So really simple stuff that you can do yourself. And then all you have to do is export as an STL file, and then pop it into Cura, and then you can go and do your slicing. Now, as far as 3D printers go, I'll just give you my 2 cents in having used a bunch of 3D printers. The things which I would recommend you look for in a 3D printer would be having something which is an open source platform. So where the actual entire printer design and software and everything is truly open source. And the second thing would be having a large community around it. So if you have those 2 things, like an open printer design and a large community, then you'll be pretty successful regardless of which 3D printer you buy. And there's a bunch of them, and they vary in like different features and performance. Like this one has a heated bed, which is really nice. So I don't need to use glue. And when the print cools, it just pops off the plate. A common problem with 3D printers is getting your prints to not stick on the plate. So heated beds are really nice for that. The Ultimaker happens to be, meet those 2 criteria. There's a really good community around it. That's how I knew about the crazy, what's it called again? Atomic clearing method. And also, it's a completely open source design. You could build one of these yourself if you, had all the hardware and the machine to mill out the case and all that stuff. Like an anti-example would be our friends at MakerBot, because they've increasingly been kind of a closed source company. We actually have a couple of them at Oracle, which we use for demos. And they spend more time in repair than they do actually working. And we're just in time. Our 3D print has finished. Does anyone want to come up and help me extract the 3D print? This is fun. You get to pop it off. Yeah, OK, come up, sir. And actually, let me check which one this is. OK, I believe this is the Model B case, Model B+. Does anyone have a B+? Do you have a B+ Raspberry Pi? No? Anyone in the audience have a B+? OK, so it's yours when you come up later. OK, so it's done printing and it's cooling, but you can probably wrench it up a little bit before it cools just by grabbing the tabs and kind of yanking it up. And start at one corner, and it should just start popping after a while. It's pretty hard to break it. You can put some strength into it. So usually it takes about, I don't know, 3 minutes to cool to the level where it will just naturally pop off. So, there we go. Excellent work. Give this guy a round of applause. Your first successful 3D print. All you missed out was pushing the button on front, which said do the print. And would you mind delivering it to, who's the gentleman? Yeah, with the hand up there, as the prize for the session. All right, so Jim, come on up. So with that, I hope you guys enjoyed the presentation. Oh, wow, that car is still going. That's a new record. I hope you guys enjoyed the presentation as much as we enjoyed giving it to you guys. And thank you very much for coming to our Devnexus talk.
Thank you.